Okay, so let's take a look at the Atwood machine problem. So the first thing we're gonna do is just assume that the pulley is massless and frictionless, and kind of remember what we did with that. So what we would have done last semester with a massless frictionless pulley is we would have assumed that everything on the string has the same tension, and we would have assumed that the acceleration is the same everywhere, so that this block, when it starts to fall, will have the same acceleration as this block as it starts to rise. We would have written, we would have drawn free body diagrams. So we would have said that the gravitational force of the block here and then is bigger than the tension force. We would have said that the tension force over here was the same. And then we would have said that the gravitational force for this guy is smaller. So that way this guy would accelerate upwards and this guy would accelerate downwards. So we would have written a net force equation for block 2, or block 1. Let's start with block 1, Fy. I'm going to assume the positive direction is in the direction of the larger force to create a positive acceleration. So I'm going to write Ft minus Fg1 is equal to m1a. I would have written a net force equation for this guy. So I said the net force in the y direction for block 2 would be, in this case, I'm going to define the positive direction as down. So Fg2 minus Ft is equal to m2a. And remember, the whole purpose of doing that is so that a is a scalar value. It's not a vector value, so it can never be negative. A is always going to be a positive value. Otherwise, that will cause sign errors along the way. So then I would have subbed in for the gravitational forces. I would get Ft minus m1g is equal to m1a. Over here, I would get Fg2 is going to be m2g minus Ft is equal to m2a. I would solve this equation for tension because I'm looking for the acceleration. I could be looking for tension. In this case, I want to find acceleration, compare what it's like when we consider the pulley. So I get Ft is going to equal, let's see, m1g plus m1a. I would then take that and sub in over here. So I would get m2g minus, be careful of the parentheses here, so you don't forget to distribute, is equal to m2a. I would then distribute the negative. I would then get the a terms on the same side. I can pull out a g over here. That's going to equal m1 plus m2, and the a will factor out. So I'll get a is going to be m2 minus m1 times g over m1 plus m2. Okay, so that's what I would have gotten for the linear acceleration. And this would be Newton's second law, because that would be, the acceleration would equal to the net force over the total mass. And that's the net force of the system. Okay, so that's what we would have had. And this total mass is representing the overall inertia of the system. So we would have been able to completely neglect the pulley. So that's just a reminder of what we've done in the past. And I know what's kind of crazy is this was a hard problem for you guys at the start. So if these are still hard problems for you, adding in the motion of the pulley creates even more algebra, more equations, more things going on. So I do suggest, if you were not able to solve Atwood machine problems in our dynamics unit, that you practice linear Atwood machines and then come back and try the rotational ones, because it's much more complicated. All right, so now we're going to work this same problem, but now we're going to assume that our pulley is a solid cylinder, and the string's going to rotate without slipping. So that means that the string and the rim of the pulley are going to travel together. We are still going to assume that the blocks have the same accelerations, but now the pulley is going to have an angular acceleration that we have to take into consideration. This also changes the way we handle our tensions. So what we have to do here with our tensions is we have to assume that over here, when we look at the pulley, that there's a tension acting on this side of the pulley and there's a tension acting with this side of the pulley. And they actually have to be different tensions. And because I'm assuming that this thing's accelerating this way, tension 2 actually has to be larger than tension 1 because I need to have the torque essentially due to tension 2 larger than the torque due to tension 1 in order to have an angular acceleration. So I'm going to call this FT2 the same as this FT2 here, because one thing we do assume is that at least in this section of the string, the tension is the same everywhere. And then actually what happens is the tension is going to decrease around this radius so that your tension is smaller over on this side. But we're going to assume that that tension 1 is the same as this tension 1. So everywhere in this section of the string, the tension is the same. And then I'm going to have to make this guy here even smaller just to better represent the fact that tension 1 still has to be bigger than gravitational force 1. Tension 2 still has to be smaller than the gravitational force 2. So then what I do is I need to write the equation for the net force on each of my blocks like I did before. So net force of Y1 is going to be FT1 minus FG1, and that is going to equal M1A. So that is actually the same as it was before, except for this is going to be a different value of tension. And then for the second block over here, I'm going to have the net force on the second block equal to the gravitational force, because that's the larger force, minus FT2 is equal to M2A. So once again, that's to keep acceleration as a constant. And then I need to consider the pulley. So the net torque on the pulley is going to be largest over here. So I'm going to create the torque due to FT2 minus the torque due to FT1 is equal to I times alpha. And then I can also still remember that I actually do have a fourth equation, that the linear acceleration of the string is equal to the linear acceleration of the tangential speed of the rim of the pulley, which is equal to r times alpha. And since we just use the variable a for that, that's just going to tell us that a is equal to r times alpha. So we'll be able to use this additional equation to help get everything in terms of a, which is what I'm looking for. So I'm going to start by plugging in my variables that are known over here. So for FT1, that's still unknown. FG1 is going to be M1G, and that's going to equal M1A. Over here, I'm going to get M2G minus FT2 is equal to M2A. And then over here, the torques are going to be at 90 degrees with the tension and the radius. So this is just going to be FT2 times R minus FT1 times R is equal to I times alpha. And I'll have a lot of room right now, so I'll sub in for my moment inertia of that solid cylinder in a minute. So when I go through and look at what's going on here, the first thing that I notice is that that should be an FT1, is that I have FT1 as an unknown, I have A as an unknown, FT2 is an unknown, and then alpha and A. So basically I have four unknowns. I have FT1, I have FT2, I have linear acceleration A, and I have angular acceleration alpha. My moment inertia is going to be 1/2 m r squared for that solid disk pulley. So those are actually known. So I do know my moment of inertia. So I need four equations, and I have four. I have 1, 2, 3, 4 equations, four unknowns, which means that with this setup, I can solve for any of these four variables. So if this question asks me for the angular acceleration, I could find it. If it asks me for one of the tensions, I could find it. I could find every single one of these variables with this same setup. So even though we're going to find linear acceleration here, you could find any of those other items if we had wanted to. So because I'm only looking for the linear acceleration, I need to eliminate all those other variables. So I'm actually going to use my torque equation here as kind of the foundation, because it actually has most of my unknowns in it. What I'm going to do is I'm going to solve this equation for tension. So that's going to be M1A plus M1G. I'm going to solve this equation for tension. So I'm going to add that over, so I'm going to get M2G minus M2A, because I add the FT over, subtract the M2A. And then I'm going to take those, and I'm going to actually sub them in over here into my torque equation, but I'm going to do that down here. So I'm going to have F2T times R. So F2T is this guy. So that's going to be M2G minus M2A times R. Minus FT1, which is going to be M1A plus M1G times R, is going to equal my moment of inertia, which is 1/2 M R squared times alpha. So the first thing that I will notice is that I can cancel out an R from each term. And then what I'm going to do is I'm going to sub in for alpha, that alpha is going to be A over R. So we're going to get over here that M2G minus M2A. I'm going to be careful to distribute my negative here. That's going to be M1A minus M1G. That's one of the biggest mistakes that people make, is in distributing negatives. And that's going to equal 1/2 big M, so that's the M of the pulley, R, and then alpha is going to be A over R. So actually this R is going to cancel out as well. So just kind of like in the previous example we did, the actual radius of this pulley doesn't matter. So if they didn't give you the radius, that'd be perfectly fine. You'd still be able to solve this problem. So simplifying it down, let's see, I'm going to group my G terms together. So I'm going to M2G minus M1G. And then I'm going to add my A terms to the other side. So that's going to equal M1A plus M2A. Plus, I already had a 1/2 big M times A. So then I can pull out a G over here. So I get M2 minus M1 times G is equal to M1 plus M2 plus 1/2 big M times A. So solving for A, I get M2 minus M1 times G over M1 plus M2 plus 1/2 of big M. And then that would be the answer for the linear acceleration. So I'll be able to plug that in. Now, if I compare that to this guy that we solved before when we neglected the pulley, that acceleration was M2 minus M1 times G over M1 plus M2. So comparing these two, I notice that the numerator is the same in both cases. The numerator is the net force on the system. Well, the net force on the system is still the difference between the two gravitational forces. Because essentially, if my system is the two blocks in the pulley and the string, then these tension forces are actually internal to my system. So they are not in part of the net force. And then the denominator is always inertia. So it's net force over inertia for Newton's second law. Well, in this case, my pulley didn't have any inertia. Well, it had some linear inertia, but because it wasn't moving linearly, its linear inertia didn't come into play. But now because it's rotating, this 1/2 M term comes from the rotational inertia here of that pulley. So if this had been a hoop, that would have been a 1. If this had been a solid cylinder, it would have been 2/5. It would have been a hollow cylinder, it would have been 2/3. It would change. So that gives you a feel for being able to predict what different Atwood machines could look like. Especially you need to kind of go back and look at what some of the other ones are, because you could still do the ones where your pulley is on the table. So you could have, you know, your block M2 here, M1, you could have your pulley passing over, and then you could have your radius R here and your mass of the pulley. And then your pulley here could have mass and do any of those situations. So any of the situations that you looked at first semester can now be done adding in a massive pulley.